Hi, Hari. So Sundar, we are still waiting for others to join.
Yeah,
Just let me know when we are going to start, okay?
sure, I'll do that. You want me to call you or what do you want me to
No,
do?
no, no, no. Just speak up,
Okay, yeah, I'll do that.
okay?
Yeah,
I'll be, doing something else.
sure, sure.
So I may not monitor if everybody has joined.
I'll tell you when. Sure.
Yeah, just tell me.
Yeah. Vasant Shiva has joined.
I think most people have joined.
Yeah, Shiva is still. I'll just give him a
Yeah,
call.
other than Shiva, I think everybody else is pretty much here. So let me know.
Shiva will join within the 2 minutes.
Okay.
Okay.
Okay. Shiva has joined.
Yeah, I think we can start.
So should we start?
Yeah, we can start, sir.
Okay. So what I will start today is with the responses you have given. Okay. So
Yeah.
let me quickly project. Okay. So I think almost all of you responded back, so that's very good. And it also gives me a sense of, what you guys think, etc. Okay. So there was this thing, the dense number sets, which are fractions and rationals and reals. So dense sets are those where in between any two numbers, you can find one more number of that kind. Okay. So any set, including fractions, will be like that. So the question is, are they countable? They actually are. They are not uncountable. There is a way to list them, even though it may seem kind of counterintuitive. Okay. So what I will do is all questions related to countable and uncountable. I'm going to send you some resources, videos. There will be, I think, one video, Wikipedia link, and maybe an associated video, etc. And go through that. And if you have questions, and 2 articles. So once you go through them, etc., after that, if you have questions, we will take them. Okay. So then there is this whole thing. Okay. When you are talking about negative numbers, does aggregation make sense? Because think about it. Aggregation is basically 2 collections put together. So our collection of negative things usually do not make much sense. Okay. We do work around it pedagogically speaking, but beyond classrooms, it has it doesn't have too much meaning. Okay. Same goes for partitioning. I mean, when you partition something into 2 parts, I mean, both the parts have to be positive, right? So you can't partition 2 things into a positive and a negative. So in a commonsensical way, it doesn't work with negative numbers. Similarly, reduction. I mean, can you explain subtracting a negative number with reduction? And I'm posing all of these as questions. Okay. So if you think you have a very good argument for something like this, please write. And I would suggest that you write to all, okay, all of us, so that, it's a shared dialogue. Don't write only to me. Okay. So maybe you have a good way of looking at it, which, we haven't seen. But till that happens, usually, I mean, reduction so far doesn't make sense in terms of subtracting a negative number. Okay. Cartesian product. I mean, you are essentially counting. So in Cartesian product, all you are doing is you are counting different ways, right? It's a combinatorial exercise. So how does negative integers come in, or any negative numbers come in there, or even fractional numbers come in there, right? So these are things you need to think about. Now, similarly, when you are dividing by a fraction, okay, and you talk about equal grouping. So you have a fraction and you are dividing by another fraction. I mean, if you're talking about 12 divided by 3, it will mean, in terms of equal grouping, you mean how many groups of 3s can you make from starting with 12? So you can make 4 groups, okay? But if you try to extend that same analogy, then does it make sense when you actually have 2 proper fractions? So think about it. Then comes equal sharing, okay? And with respect to equal sharing, it can be done actually, but it is not so direct, okay? There is something called chocolate plate model, which I think I may have shared with some of you. If not, I'm going to share again. So just take a look. It's probably 1 page, so not a big thing, and and see if that makes sense. Chocolate plate is the most robust model that I know to robust way of modeling division with fractions. You can put any kind of fraction anywhere before or after the division side, including improper fractions. That's why it's robust. Now, here is the last thing, array. It does make sense for negative numbers, but you cannot use it as the starting point. You need to first establish that negative times positive is negative, positive times negative is negative, and negative times negative is positive. Once you establish these three things, the three possibilities of multiplication with negative numbers, then you can use the array. Okay, and you can use array of signed counters, colored counters, or you can use use array in another way of signed area. You can do that, but it's not the starting point. You have to establish those three. Okay, now how to establish those three? NCERT class 7 textbook integer chapter does a very good job for integers, but I'm not sure if that can be extended directly for rational numbers because it uses tables, and tables by nature are kind of discrete, right? I mean, the underlying thing about tables is repeated addition, so there is a discreteness in that, and integers are discrete, so it works very well for integers, but then it can't completely, uh, do justice to even all rational numbers. Forget the real numbers. Okay, so that is where scaling actually does help, and that requires a kind of projection kind of a thing. So I will try to show it later today. If we run out of time today, definitely on Friday. Okay, so but this is something that we will definitely look into. Okay, now the other thing, okay, we'll get to that when we come to that slide. So this is a general sequence that uh, is recommended when you teach numbers in particular. And the first three are usually ignored. Okay. Uh, so the first one is, why do we need this kind of numbers? Okay. And there are in the need, there are usually two parts. There is the, why do we need it in life? And why do we need it mathematically? Now the life part again can be broken into two parts. Uh, why do we need it, or where do we need it in day-to-day life? Okay. And then why is it needed for, say, certain jobs, certain professions? And the answer is going to vary. Okay. So not everything is needed for all professions, etc. Somebody who is basically using money, they don't necessarily need to go beyond rational numbers. Whereas somebody who is an engineer or an architect or is doing something which involves meticulous measurement will probably need to get into irrational numbers. Okay. I mean, simple thing is when you hit pi, when the anytime you have to get accurate measurement of anything circular, you cannot avoid pi, and pi is a very, very irrational number. Okay, so there is that distinction. Um, and then of course there's the mathematical need, and there can be a curricular need also, in terms of why do you want something, etc. See, for example, why do you need square root? one need is also that when you get to trigonometry, you can't avoid square root. Okay, and at the heart of anything to do square root, at least for me, turns out to be Pythagoras. So if you don't like square roots, if you are very comfortable with rationals and you don't like how it becomes messy with reals, blame Pythagoras. Okay. Uh, but it's very important that as teachers we know the need, because sometimes word problems are created in certain chapters to connect math to real life, and sometimes they are damn artificial. Glorious example is HCF LCM. It's there because without that you cannot work with fractions and then rational numbers, etc. But so there is a mathematical need primarily why that is there in the syllabus, HCF and LCM. But if without understanding that, if you force it to look like, oh, it applies to real life also, it really becomes very artificial. Okay, something I felt as a child and I still feel now. The next part is making sense of what these numbers mean in terms of what quantity they represent along with their names. Terminologies like what is a numerator, what is a denominator, what is a base, all those things kind of come in. Writing them numerically, that's where rules and conventions come in. So we will spend a bit more time on both all these points. And these are where we don't spend adequate time usually. But if it is spent there, once the meaning is made, and in terms of all these things, including how the symbolic aspect, then the next part, playing with them. And by playing, what I mean, I have completely listed out basically the operations. Those become much easier. Okay, and of course, comparing doesn't have to be deciphered more, but what do you mean by adding, subtracting, multiplying, dividing? Those do need to, and that's why it was one of the homeworks. So we will go into those more. So let's do that. So I'm going to open it up right now. So do speak up. So why do we need whole numbers? Any thoughts, any ideas? Yes, Sundar.
Uh, it's just I don't know. Uh,
So one popular story is that, people used to have cattle or sheep, and you had to take them out for grazing, and beyond the point, people would delegate those out. So how do you ensure that if um, 30 sheep were taken out, all 30 has been returned? How do you keep track? Okay, so that kind of necessitated uh, numbers, whole numbers which are used to count. Okay,
yeah.
and then zero came in for various reasons. Definitely as placeholder in terms of writing numbers in a place system, and also in terms of operations. Okay, so if you take away 3 from 3, what is left? So that also is there. So that's whole numbers. And I'm going to skip the whole number part a bit because that's not something you deal with so much, right? Fractions. Why do we need fractions? Anybody?
To represent something that's less than 1.
Yes, when you are trying to measure, okay, and you have some unit and you are trying to measure another quantity, with that unit, what if it falls in between? Okay, so it's more than 7 units, but less than 8 units. So what do you do if it is something in between? Okay, and measurement often generates, continuum. I mean, length is very easy to imagine in that sense. So something which is between, let's say, 7 feet and 8 feet. How do you quantify that, right? So that's where the need for fractions emerged, and that is there. Integers. Do you want me to give this out as another homework? I can do that, or we can finish it off now.
We can finish it off now.
Okay, Ranjit had unmuted himself. Yes, Ranjit.
Maybe this is came because of vector operation, like measuring, representing direction.
Yes, but vector is probably came a little later. Um, if you think in terms of profit loss, that is one part where it really kind of comes in. If you think about it, loss is nothing but negative profit, so to speak. So that's one place where integers really make sense. I forgot to mention this, but mathematically, fractions also fill the void. It gives the closure under division. Similarly, mathematically speaking, integers provide closure under subtraction. So for both, along with the real life need, there is also the need for, there's a mathematical need as well. Okay? So rational numbers. So now you have to give an example where integers won't cut it, you need something more. Any thoughts? I didn't hear you, Vasantaraj. Can you please repeat that?
Swati, please repeat the question. I didn't.
So can you think of a need for rational numbers? Why do we need rational numbers?
For comparison, like ratios.
Comparing, so that give me an example where fractions or integers won't suffice and you need rational numbers.
Swati, if you dealt with the integer is in the negative form, it's useful. It's like
See, when it is money, profit, loss, etc., you can think a bit in terms of discrete, okay? Because money will have a minimal unit. So, you can think in terms of rupees or paisa and have it completely discretized. However, when you are thinking of depth versus height, so there is a well or a pond or an ocean or something, and the water level you take as 0, and beyond, above that, you think of it as height, and below that it's a depth. Then you are measuring, essentially you are measuring length, so to speak, or distance. But then it has also got direction, below water or above water, below a certain level or above that level. So then that direction aspect comes in, and that's where just integers won't cut it. So you have the same need you had for fractions, and because there is the direction thing aspect, you need to stretch the number sets to rationals. Mathematically, when you want closure with respect to both subtraction and division, you need rational numbers. Okay. So with just 4 operations, once you get to rational numbers, you are in a very comfortable state. Okay. And that's where it kind of stops. But then math has a tendency to grow. You can see that the real number comes with a little gap. So to understand the need for real numbers, that is when you have to go beyond rational numbers, mathematically speaking, you need a new operation of exponentiation and the reverse of it. So if you think of exponentiation as something like a to the power n, you are still within rational numbers as long as n is positive integers or negative integers, no problem. But the moment that power, that index becomes a rational number, and you kind of are looking for the inverse operation. See, so far the operations we have, they are all paired. Addition, subtraction, opposite of each other. Multiplication, division, opposite of each other. So when you have this exponentiation, and you start it with repeated multiplication, or then you extend it to repeated division, then you can think of the inverse function, so to speak. And that inverse function is connected to search. So that's one place where you feel the need for stretching your, mathematically you need to stretch your number line there. In life, again, I mean, the first instant is again kind of related to Pythagoras. Length is one quantity which we can measure very closely, very minutely. And when you try to measure the diagonal, measure the length of a diagonal of a unit square, that thing turns out to be irrational. That's not rational, right? And again, it comes from Pythagoras. The diagonal of a unit square is √2. So if you want to measure it accurately, very accurately, rational numbers won't cut it. Okay. And the other irrational number I have already mentioned. The moment you try to do stuff with circle, pi. So that's where real numbers come in. It's very, very closely related to measurement and mensuration. Okay. Okay. So now I have tried to capture whatever I have said so far in this slide, and I have left the real part deliberately blank because it's not a straight direct jump from rational to real. You have to bring in an operation, its inverse, and then comes real. Okay, so it's a bit complicated, and in fact, root 2 and all the surds will come in through this exponentiation and the roots, but it will still not catch pi. So pi is a different creature altogether, and so those will be taken up if we have time, or maybe after you go through those things I sent you on countability, etc. Some of them are pretty fun to read, okay, with lots of cartoons and doodles and stuff. Okay. So, and I'm going to share the PPT today. That's used today. So, right. Okay, good. Now, in terms of meaning making, these are the different things that you can use. I mean, these are the recommended things, and you can see kind of certain parallel. So for whole numbers, you can start with counters. It can be anything that you can count: buttons, pebbles, bottle caps, anything. Okay. Now I know that you have used the discrete model for fractions. So if you wanted to show 3/5, you will make a collection of say 5 stones and separate out 3 of them. So that's 3/5. Okay. So that's what I'm talking about in terms of discrete. In integers, again, you have widely used colored counters. So counters in 2 colors, one color representing positive, another representing negative. Now, this colored counters can be extended to colored length, and that will work combined with number line for rationals and reals. Okay. Notice that when you get to rational, you lose both discreteness and quality. So, your choice gets very limited there. I think you are probably familiar with Ganitmala. In the next slide, I will show you and talk a bit about that. So Ganitmala has to transition into number line, and it will have double, so the Ganitmala represents only the positive part of the number line, and the double that represents both the positive and the negative part. That's the double. Okay. Similarly, for fractions, fraction strips, which can be used to make a fraction wall, can be the precursor before into number. And important because when you hit rationals, you don't have much of a choice other than number line. Okay. So again, I'm going to show you pictures of fraction wall and number. Other than that, there are certain things which kind of stand on bundle sticks. Very important pedagogically to use at all, but doesn't extend much more later on. Again, circles as the whole is a very good starting point for fraction for various reasons. But again, it does link very closely to pie charts, direct linkage, and it can also help with trigonometry, possibly to an extent, especially if you get to fracking. But still, I mean, it's very good starting point, but doesn't extend as well as counters and number line does. On the other hand, flats longs units, again, I'll show you pictures, extends very nicely. So it will get into decimals, and then it actually gets into algebra also. And then if you take the 1 in a flat unit is the shape of a square, and that square as a shape is extremely powerful. Okay, it's also the basic unit used for area. So and to make sense of that, when you partition that square for fractions, it really helps a lot. In fact, all the benefits of strips is there in square and more, because a strip is a long in rectangle, so you can split it only in one way, you know, along the longer dimension. Whereas square you can split it in both ways, right, vertically and horizontally. That makes it extremely powerful, especially when it comes to multiplication. Okay, so we and the last one, arrow cards, is very helpful to understand place value. So it's helpful both for whole numbers as well as for decimals. It extends there. I believe you are familiar with it. If not, again, I will share some things, but I have not included in this slide. Okay, so these are Ganitmalas and number lines. Now, if you notice, the top black and white one is a single Ganitmala, and you can see it goes from 0 to 100 and the corresponding number line. Now, notice that number line and the number line below, there are some differences. You can say one difference is that the second number line doesn't start from 0, but that's not the main difference. If you look at the number line in the middle, which has an arrow, you notice that it is actually not very scaled. Okay, I mean, now that I look at it, it looks actually pretty scale. But what I'm trying to say here, the relative position is more important, not whether 333 is exactly at the right position in between 300 and 400. What is important is that it should be between 300 and 400. But whether it is closer to 300 or closer to 400, that part is not so important. This kind of number line is called open number line, and the scaled version is called the closed number line. The scaled version, of course, has many advantages, no doubt about that. But the empty one, the open one also has a lot of advantages when you are trying to add, subtract, and do various other explorations. Okay. The bottom number Ganitmala is a double Ganitmala. You can see that it's made out of 4 kinds of beads, and below it I have tried to place the whole number line, positive and negative part. Now, because it was a picture taken, the amount matched the picture so well, but it kind of gives you a sense of how the Ganitmala is related to number lines. This is fraction strips. You can see the fraction wall on the left, and you can see how there is a number line in each line. Okay, and it's a good, fraction wall after all is a static picture. You can't move things around. So that is why, you know, the fraction strips that is there on the right, they are of two kinds, as you can see. In the top part of the whole strip with the unit fraction marked, and you know, one unit fraction shaded out of the all the partitions. So it gives you, it's very helpful to introduce unit fraction and can be useful later on also. But again, that self is not enough. You need the smaller pieces. So you need the separate halves, the separate 1/3, and the separate, you know, 1/5, etc. The color scheme that you see here has evolved over time. Once I share this with you, if those of you adventurous, you can try to find the logic behind this color scheme, and you know, feel free to share your findings and we'll see if you got it. Okay. It came out of using something minimally and turned out to be mathematically rich. So, okay. Oh, hang on 1 second. It looks like an unwanted animation here, so let me get rid of them. Okay. Okay. So flat longs unit, you can see the flat which is the 100, the long which is the 10, and then the small square which is the 1. This, as far as you are dealing with whole numbers, this is the most powerful manipulative. It can be used at upper primary level to talk about squares and square roots. Okay, very, very powerful, especially if you want to understand the division algorithm for finding square roots. It can be a very good starting point. And then you can see how that tiny square is blown up for fractions, and how, you know, 2/5 has been represented, right? And lot of things can be done. And I remember having with it something related to fraction square. So if you don't have it, let me know and share it. I think I don't need to, because everything is there in that Google Drive. So, and this flat slungs units actually generalize to algebra tiles. Okay, so that's the picture of algebra tiles, and whatever you can do with flat slungs units, you do with algebra tiles. So addition, subtraction, multiplication, division. What I like most about algebra is middle factorization. Okay, that's when it really gets very interesting. Okay. Now coming to the third part in terms of writing numbers, etc. That's where you have these are the rules and conventions. So for whole numbers, the number names up to 10, 20 are pretty arbitrary usually in most languages. The numerals till 9 are arbitrary. So that's why they vary from language to language. But once you get to 10, 2-digit numbers, etc., then the base system in, so there are, you know, certain rules. Similarly, you know, as you can see there, for each one is some convention and some rules. So it's a good idea to be very clear about which part is convention, which part is rule. Okay. Okay. So, and what I forgot to mention here, I'll modify it for sending it to you, is that is where it becomes completely unbounded the moment you get negative. Okay. So, you know, this chart give us some sense of what is happening, etc. Now, this is the slide that kind of consolidates the meaning of operations. And as I said, the moment you get real numbers, aggregation usually doesn't work. Okay. Now, in the case of reals, you notice that I have kept it with the caveat positives only, because some, okay, and then you have the flat plane surface area, which is the circle, that again has another pi in it. So again, a very real number, not rational. And I'm assuming the height of the cone and the radius of the cone to be rational numbers, to be either whole. I mean, let's take them to be positive integers, okay, to make sense. So here, to get the total surface area of a cone, you are adding two real numbers, and it is actually completely in the aggregation sense. Here is some area, here is some area. You combine them to get the total surface area, right? So aggregation does play a role, but only in the cases where both quantities are positive, okay? Similarly, you can say that, where reduction and partitions are kept, okay, with the, disclaimers or with the mention of where they work or where they don't. Similarly, scaling works throughout, but equal grouping doesn't necessarily always work. Again, rate again doesn't necessarily always work. The negativity comes in. So those are things you have to kind of think with a bit of a bit carefully. Okay. So that's kind of that in a nutshell. Now, this slide is kind of important because this can be kind of baffling for students, because they're used to something, and when they encounter new number sets, it becomes very counterintuitive. And that is where, as teachers, we need to draw their attention to these. And this is where you can ask them to give example of each cases, like give example of an addition involving integers where there is an increase. Give example where there is a decrease. Same thing goes, like in case of multiplication and division, it bifurcates into 4 possibilities. Increase in quantity and magnitude, decrease in quantity and decrease in magnitude, and then if you're talking about negatives, then decrease in quantity sense, but magnitude could increase or decrease. Okay, so there are 4 possibilities, and of course, it can stay the same or something like that. So as teachers, you can ask them to give different examples for each case. Okay, you can quiz them. Does it always increase? Can you give a counter example? Now, if they say, oh yes, of course it will always increase, then challenge them with a counter example and see what happens. Okay. Now, if they get it, then ask them for another such counter example. Okay. So that way, pedagogically, this part is important, because then when they come up with examples and counter examples, they gain a level of clarity when things increase, when things decrease, what is going on. Okay, so it helps them to expand their notion of how things behave. Okay, so I'm not going to discuss properties today because I want to spend some time to discuss stuff, but let me share this scaling thing. I may have shared it earlier, though I'm not 100% sure. Okay, so just give me a moment to open that PPT. So the basic idea is that of projection, and you can start with whole numbers and then build up. Okay, and it can start as a dot sheet activity. So this is the thing. The basic principle is the projection dilation kind of a idea, and yeah, you can deal with reals up to rationals. It's perfectly possible. For real numbers, it's best to go through GeoGebra, because there you can sketch it and you can just move things around that will kind of continuously do stuff. Yeah, so let's get to it. So you have this number line, and this is what you are going to scale up or down. And the second number, the vertical one, is the scaling number line. So you know that 1 is the multiplicative identity. So that is why the 1 of the scale factor is coinciding with the 0 of the original number line, which is going to be scaled. So now, if you choose the factor to be 4, you draw a corresponding number line, and this is how you see how the original number line has got stretched. Okay. So now if you look at this, these things about what happens when we multiply by 0, etc., always comes in place, because you can kind of get a sense that as this 4, instead of 4, if you had taken 8, you kind of get a sense that the stretch would have been more. If instead of 4, if you had taken 3, the stretch would be less. And if it was 0, I mean, everything will collapse to a point, right? And if it was 1, then it will remain where it is, multiplicative identity, right? So you kind of can have a rudimentary sense that in between 0 and 1 is where it shrinks, and that will help with fractions. Now you can't do fractions on a dot sheet, but you can try decimals and a limited range of fractions, so to speak, on graph sheet. Okay, centimeter graph or inch graph paper, you can try that. Let me know if I have not shared a write-up with you on this, and I will do that. Okay. Now the question is, what happens with negative numbers? So you have the full number line here, and you have the full number line here too. So this is the part that we already know, right? Now what happens to the negative part of the number line? Very similar, like that part also gets stretched in the same way. Okay, no surprises there. Kind of makes complete sense. Now, what if we take a negative scale factor? -3, that's what we have taken here. Now let's see what happens. Now when we multiply positive numbers, see it has gone over to negative side, right? It switched sides. And what happens if we multiply negative numbers? They also switch over to the positive side, right? So when you are multiplying with a negative number, it changes sign. That comes out pretty clearly from this. And with GeoGebra, you can actually make the scale factor vary. So fifth now, yeah, so let's see what happens here. Okay. Kind of gives you a sense of, you know, a rotation, okay, about that blue 0, scale factor 0. And similarly for the, you can get a sense of that whole thing has been just flipped over. The positive has gone to the negative side, the negative has gone to the positive side. And the flip that we use in a double-sided algebra tiles kind of corroborates with that. Okay. There are more fascinating things associated with the flip, but I'm going to restrict myself to that. The thing is that what I have shown you is for integers, but basically we are playing with number lines. So this can be extended to rational numbers and real numbers, especially if you do a GeoGebra sketch. I am trying to see if I have any GeoGebra sketch. Unfortunately, I don't. So let me pause for now. Okay. So that's all what I wanted to share with you today. And now open to questions, etc.
Hi Swati, this is Shriman.
Hi Shriman.
Hi, sorry, a lot of hiccups, but I finally joined, so I'm just listening in and trying to understand. Yeah, just thought I'll introduce myself.
Thank you.
So you will be sharing these slides? So
yes, today's slides I will be sharing.
Okay. Were there slides from the last session which I didn't realize was there? If there is,
no, I did not share the last time slides, but I think these kind of incorporate that, and the homework that I had given, that, I mean, between that and today's slides, it kind of gets captured.
Okay.
Also, there are a lot of things which have already been shared in the Google Drive. So, so I'm not going to share those unless you ask for them. So fraction squares, I know it has been shared. Chocolate plate, I think I have shared it, but if not, you guys let me know. Okay. So that I am going to, basically I'm treating you as adult learners. So if you need something, you ask. If I have showed something and I have not given you details, ask. No spoon feeding.
So I guess I'm just probably going to ask one of the others in the call if this drive is the same drive that all of us have access to in terms of some of these other things.
Yeah, it's the same drive.
Yeah.
Okay. All right. Sounds good.
Hi, Swati. This is Shiva.
Hi.
So I have some doubts.
Yes.
You said in multiplication, if you multiply two numbers, integers, it always increases.
No. I don't think
The
I
table
said that.
Okay.
I mean,
Can you
it
show
can't.
the PPT? Okay.
Yes, I'm going to get to that 1 second.
Yeah.
Yeah. So multiplication, integers, magnitude increases except for 0 and except when you are multiplying with 0 and you are multiplying with 1.
Okay.
Magnitude increases, not the whole thing.
Okay. Okay.
Okay.
Okay. Sorry. Yeah.
But I'm glad you asked.
And one more thing. So you have shown that last slide about how to do the multiplication on the dot lines.
Yes, dot sheets, yes.
Yeah. Is it possible to do the division on dot lines?
Actually, yes. You can do it because it's the reverse thing. So what you need to do is you first, so okay, let me switch to whiteboard. Okay, so let me take a very simple example of, let's say, 12 divided by 3. Okay, so what we'll do is we will first draw the vertical number line. So that's 0, 1, 2, and 3. Okay, so now you first draw the number line through this 3. Okay, and you locate wherever is 12.
12. Okay.
Okay, so you have got both the dividend and the divisor.
Yeah.
Right? Now you draw the number line through 1. Okay, and you connect this 12 to this 0.
Okay.
Okay, and I mean, this is very roughly drawn, but it should ideally cut at 4.
Oh, okay. Okay.
Okay, I mean, you can see that from the proportionality, right? From similar triangles aspect, you can kind of get a sense of it, but when you do it actually, it works.
Okay.
Yeah. So it's a pretty strong tool that way. So this one, I'm not sure if I have, I don't remember right now, whether I have added the division part to it. I'll double check, and this is something I probably need to share. Okay.
Okay, sorry. Thank you.
I'll just check and see.
Yeah.
So when you are, frankly, I don't know any other way of making sense of multiplication and division with rational numbers. Because, you know, when you have to multiply a number by, say, negative 3/4, what does that really mean? Multiplying a number by 3/4 is, you can understand. You have this whole quantity and you kind of chop it off in 4 parts, so you know how much is 1/4 of that quantity, and so then, you know, you scale it up by 3. That makes sense. Okay, I mean, there's a process of doing it and you kind of have a sense of what it is. But when it becomes negative 3/4, then what? So I found that this way you can make sense of that. I mean, creating a GeoGebra sketch of this is very simple, very simple, frankly. You just have to draw 3 lines, so to speak. And one of the line is already there. So the vertical line is already there. Okay, hang on. Okay, so the vertical line exists as it is. So we start with, oops, sorry. So that's the base number line which gets stretched. Now you want to add a point on this vertical number line, which will be the scale factor, which will indicate the scale factor. So it moves only along this. And you need to draw another line through that. So that's the scaled number line. And you need the origin. And then you basically pick any point on this number line, right? And you join these two, and wherever is intersects, so that intersection point, this is basically the product. So if let me just rename things a little bit. So O for origin, yeah, so this guy, this D here, okay, so let me call that 0, comma A. Okay. A equal to scale factor. Yeah. N equal to this number, then this is nothing but A times N. Okay, so this is A times N, and notice that as A decreases, AN decreases. As A increases, AN increases. As A becomes between 0 and 1, AN has become smaller than N. Now, it's important to note that this blue line segment, or maybe I should just make this vanish. Okay, no. Yeah, that's fine. The blue line segment is indicating N, and this pink one is indicating A times N. Okay. So you can see that AN has become smaller than N. Okay. Now, if we make A become negative, immediately you notice that even though N was positive, AN has become negative. Okay. And out here, as long as A is between 0 and -1, the sign has changed and the magnitude has become smaller. Now, as A becomes smaller than -1, the sign remains negative and the magnitude also increases, right? So all of these can be observed very quickly, very smoothly, like that. And when you are moving this A, you are going through all the real numbers, not just rational, right? And it's not that you can, move only A, you can move N also. So you can see as N goes from positive to negative, AN also becomes negative with A positive. And similarly, as A becomes negative and, N negative, A negative, AN becomes positive. So all those things can be nicely observed. And you can also see that AN grows with N. As if N is small, AN is small. As the magnitude of, okay, since I put it, okay. So, yeah. So magnitude wise, as N increases, AN also increases. As N decreases, AN also decreases. And that is there in terms of magnitude regardless. So there is the magnitude aspect also. Okay. So that's the GeoGebra part. Did that make sense?
Yes, it did.
Okay. So how many of you have played with GeoGebra?
This is Shriman. I have not. I need to play with it.
Okay. Glad that, you are interested now.
I have used more Scratch than GeoGebra, but I've also used a little bit.
Okay. So those of you who, I think many of you are more familiar with Scratch. So what I'm going to see, I showed you how to do the division thing on whiteboard. Okay. I have showed you how to do the multiplication in GeoGebra. Now combine these two and create, how would you do it for division? Okay. And you can do it in Scratch and share next time, or share it with me. I should have Scratch somewhere in this laptop, from the last time I went there. If you can do it on GeoGebra, so I'll definitely be able to see it. And so, give it a shot.
Yeah.
Okay.
Yes, sure.
It's not very difficult. So I'm not going to shared the write-up with division. I'll check. Most likely it is already there. At least the PPT should be there. So in the drive, I'll check that. So yeah. Also, I did not get time to look at your lessons plan yet, but that's definitely my task for tomorrow. So Friday, definitely I'll be done with, before I join, I'll be done with that. So I'd like to give you guys two homeworks. One is this, creating the Scratch or GeoGebra sketch for division using this scaling model of multiplication. And as you can see, this works for all combination of numbers, positive, negative, etc., all possible combinations. The other one is, now that I have shared with you, the basic manipulatives modelings for each kind of numbers, I would like you to think about how would you try to justify the properties. Okay. I mean, the formal proof includes Peano's axiom, etc., which is very complicated and definitely beyond the reach of most teachers, forget children. So is there any way this can be done, the properties? Okay, that's very much there in the syllabus, but can it be done in a way where it captures all possibilities, or it is generalizable? Not where you take any two things, you add these two, you add A and B, and then you add B and A. So every case this works, so therefore you kind of conclude that it is going to work. That's not how math works. That's a very empirical kind of way to go inductively. Okay, so we want something beyond that. So if you can come up with that, that will be good. So think about those things. You can, as usual, stick with your number sets and play around and think about what can be done for all 5 of the properties. Okay, so that's the second homework. Sundar, you were trying to say something, I interrupted. Sorry.
No, I was just thinking how to do it in Scratch. That's all.
Oh, okay. Yeah. Okay, so what I would like you to do, this is, you all have a level of teaching experience. Okay, some of you are new. So especially those of you who have teaching experiences, this is particularly for you. Can you make a list of questions and issues with respect to numbers that you have encountered? So for example, one of you mentioned, how to introduce integers. That's an issue. Okay. So similarly, if there are specific issues where you have faced any kind of difficulty, or where you have seen that children usually struggle with this, can you start making a list? So what I would ask you to do is, since you guys are on Google Drive and all, create one file and start jotting this there. So I mean, ideally create these sections for these number sets, right? So whole numbers, fractions, integers, rational numbers, real numbers, etc. And start adding questions to that. So these are the issues that you have faced, okay? And let's try to address them, okay? So I would like to get this part by Friday, okay? So that, you know, I get a little time on Saturday, Sunday to, you know, look through what all is there. Is that okay?
Yeah.
Now, those of you who have no teaching experience, you can look at the textbooks, the respective textbooks, and if any question pops to your mind, why is this happening this way? Is there a better way? Or I don't like this. So those are things also you can share, especially where you think there is a problem. It is not addressed adequately, or you found it confusing the way the textbook has dealt with it, or you remember a confusion maybe from your childhood days, okay? Anything that where you think that, you know, I know that happens, but I'm not sure why that happens or how that happens. So for you know, specifically think about those questions, okay? Now, those with teaching experiences, you may also have similar questions. So please feel free to jot those things down, okay? Okay?
Yeah.
Okay. So for Friday, we have primarily two things. One is we will definitely look at all these properties and how they can be dealt with for each sets, etc. But definitely give it a thought. And maybe you can figure out a, you know, a very nice way of coming up with doing some of this that will be very refreshing. And I think we will probably have time to discuss the countable, uncountable thing. Another very important homework, and this you can complete by definitely by Sunday night, and that would be related to this slide. Okay, so this one has all the meanings. Okay, so for each meaning, okay, of each operation, come up with one word problem. You don't have to create it yourself. You can look at the textbook and pick up a problem from there. If a textbook doesn't have something, because for example, Cartesian product is usually ignored. Very rarely you will find a problem that uses Cartesian product in a textbook, in an Indian textbook, let me put it that way. So barring those, so I would like you to come up with problems. Okay. So that's a very important homework on word problems. And I'll send you an email with all these homeworks. This homework has more time. This has to be done by Sunday. The other two homeworks have to be done by Thursday. Okay. And Friday we will meet at 10, usual time.
Okay.
So that's it from my end.
So,
Anything else?
any questions or we?
So another thing, during the when I'm presenting something, etc. If any question comes to your mind or etc., feel free to use the chat option. Okay, you can jot down your questions there, and we can take a look at them after I'm done talking. So feel free to use that also. Okay, doc.
Okay.
That's all for today then.
Sure. Thank you,
See
Shakti.
you guys on Friday.
See you on Friday.
Bye.
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 Thank you. Bye bye.
Bye.